My name is Ján Čegiň, and today I would like to present you machine learning-based test data generation for safety-critical systems, which is part of my PhD thesis. Automated software test data generation has appeared as a solution to the problem of wanting the best tests written in the shortest time possible. We focus on coverage-driven unit testing. One of the most widely used methods is symbolic execution, where we traverse the tree of the tested function, collect constraints, which are then executed to provide test data. However, many problems still exist, such as the path explosion problem, which may occur in recursion loops and function calls, where the number of possible paths may grow exponentially, and the symbolic execution has problem of selecting relevant testing paths. In model-based testing, we take the approach of collecting test data as a problem of traversing the state machine or label transition systems, and so on. In adaptive random testing, we try to guide the random testing process by dividing the space into different subspaces from which we generate the random testing data to achieve a higher coverage or faster the approach. In search-based techniques, we use heuristic or meta-heuristic approaches where we model the problem of generating test data into a search space problem and use methods such as genetic algorithm, hill climbing methods, and so on. Machine learning methods have been applied to this domain of test data generation. In supervised methods, we used labeled data to provide test data. This was, for example, used in GUI testing of Android applications, where they use a dataset of provided actions from real human testers, and their approach has gotten good results compared to that. Or we can predict possible coverage achieved by various search-based approaches, as running these approaches is often very resource intensive. In unsupervised learning, we can cluster different input data to generate new data using encoding-decoding methods, or for combinatorial interaction testing, where we need to choose different strategies. In reinforcement learning methods, we try to train an agent based on interactions with the environment to achieve a reward. In this case, the higher coverage. This was also used in GUI testing of Android applications, for stress testing of Python systems, or for unit testing based on the branch coverage. However, machine learning-based methods have not been applied to the domain of safety-critical systems, where failure of such a system would cause a significant increase in safety risk for people, environment, and so on. Systems in nuclear plants, aviation, automotive, railway, and so on belong to this category. For automotive, the ISO 26262 defines how software engineering of such a system should look. Unit testing of these software parts is done via the MCDC criterion, as per the ISO standards and the ISC standards and other different standards. Now, why would this criterion be beneficial to also machine learning methods? The MCC criterion requires 2 to the power of n test cases to be completed, while MCDC requires only n plus 1 test cases, where n is the number of conditions in the tested function. This severely reduces the number of needed test cases, helps us in prototyping and faster evaluation of our given machine learning methods. We have encountered several open research problems, which I will evaluate on further. The first one being, what are suitable machine learning methods for test data generation based on the MCDC criterion? Second, can we find a suitable solution for path explosion problem using machine learning methods? And third, but not least, what is a suitable code representation of function under test for the machine learning methods in test data generation based on the MCDC criterion? Now we have different methods that we could take in machine learning methods for this domain. First of them being reinforcement learning, which we have used previously with some success, but I will talk about that in a different section of this presentation. In here, we develop an agent which interacts with the environment, in this case the tested function, or its representation rather, being it AST or so on, using a set of actions, manipulations with the input of the parameters of the function, which would give us the needed test data to achieve a reward, in this case, as high coverage as it can. Or we could use unsupervised learning to cluster functions via similarity. Now, why would we do that? We can train a model on each of these clusters. We would deal with less diverse clusters, which would improve the accuracy of these models. We could also use new approaches like the neural Turing machine. In here, it is a neural network with external memory. In its newer iteration, called differentiable neural computer by DeepMind, it's said to have the capabilities to also represent symbolic states. However, no previous work was done in exploring these methods for test data generation in general, and it also has limited examples in different domains, but it could also serve as an interesting way of researching what can be done with this method. We could also use supervised learning, as we have functions with the test data, and we could transform the functions into their given representations and train a model to provide test data for these given representations. Then we could evaluate such model and see how good is it doing compared to unseen functions previously not used in training. Our goal is to achieve at least 90% MCDC coverage. This value is based on existing work in the field, mostly for search-based methods, which are being able to achieve this value easily. However, most search-based methods are evaluated on benchmark functions or playground examples. In our first abstract, we pointed out the problem of not having relevant datasets to evaluate these methods for the domain of safety-critical systems. We have an industrial project available, but it's under an NDA from our industrial partner in the automotive industry. We would like to use this project to create and use a synthesized dataset. We would extract statistical attributes from this dataset and use them to find a fitting open source dataset. For this dataset, we would like to randomly generate this data, which would give us a baseline for this approach, but also for future approaches. The evaluation would be done using an existing infrastructure from our prior research project, in which the transformation of test data into runnable toolset, test suite, and the retrieval of test coverage is done automatically. In our needs research question, we ask ourselves, can we find a suitable solution for path explosion problem using machine learning methods? As previously slide, we used reinforcement learning in a subset of 22 handpicked C functions to determine if it can be used. In here, we found out that we are able to achieve 100% MCDC unit testing coverage for functions with loops, external function calls, and recursion, but we failed at functions with complex decisions where lots of constants and numerical constants were present. However, machine learning methods show capabilities to deal with this problem, as you can approximate the execution of the given function under test. As such, we could maybe model loop execution to help symbolic execution in the path explosion problem. When a loop or complex loop is encountered, we could approximate which paths are viable and thus reduce the number of needed paths the symbolic execution needs to compute. However, more robust evaluation is still needed. Last but not least, we tackled the issue of what is a suitable code representation of the FUT for ML methods in test data generation based on MCDC criterion. First of all, we have the code to vec. In here, we try to apply the method of word to vec from NLP to the issue of code, where we transfer code into a viable embedding. We also could use tree convolutional networks, where we try to capture several convolutions from the AST into a subset of embeddings. Or we could use encoder-decoder methods, where on one part we have an encoder and on the other part we have a decoder. And we model the problem of representing code as a problem of translating from one part to the other part. We could, for example, translate code into test data, or just transfer code into code again, and then use the dense layer as our code representation. Or we could use heuristic methods, as was done previously for reinforcement learning for the branch coverage of unit tests. But here is the issue that if we use heuristic methods, the method will always be only as good as the heuristic is. In summary, we focus on test data generation for safety critical system, specifically on coverage-driven structural unit testing for the MCDC criteria. We have data from our industrial partner in the automotive industry. We wish to use this data to provide a dataset for a more open evaluation, which we will use. We focus on machine learning applications for test data generation, as maybe more ensemble methods can be applied. In our future work, we would like to create this synthesized dataset and also evaluate machine learning methods to further narrow the viable ones and then use them on a more robust evaluation. Thank you for your attention.